Hello everyone, and welcome back to Total Organic Chemistry. In this video we're going to be taking a look at Fischer projections as a way to represent chiral molecules, and also at something called diastereomers, whereas we've talked about enantiomers before. So first, let's look at what a Fischer projection is. So a Fischer projection, like I said, is just another way of representing chiral molecules, or molecules with stereocenters. So if we take a look at some molecule like this, we have maybe a methane, a substituted methane, and we'll draw the bonds like this, and then we have these substituents. So we can tell that this is a chiral molecule. It has a stereocenter because that carbon in the middle has 4 unique substituents. And I've drawn the bonds this way with the wedged bonds horizontally and the hashed bonds vertically to show you what the Fischer projection would be for this. So the Fischer projection would just look simply like this, with just straight lines, and the horizontal lines correspond to the bonds coming out of the plane, so towards us. And the vertical bonds are going into the plane, so behind the paper, behind the screen. And I kind of think of this sometimes as you could think of a pair of scissors. So cutting, and those vertical bonds are kind of like the blades of a scissor going into the page. So that's kind of how I would hold a pair of scissors. And sometimes that helps me keep track of where the bonds are pointing. So why do we use Fischer projections? Well, it's a lot easier to just draw those straight line bonds instead of always having to draw the hashed bonds and the wedged bonds to show the actual 3D stereochemistry of your compound. So a lot of times Fischer projections are used sometimes in biochemistry, representing carbohydrates and things like that, but we're just going to take a look at some simpler representations right now. So if we take a look at this, so this same molecule, this substituted methane, and if we rotate it 180 degrees, then we're going to look at this. So we have iodine, fluorine, chlorine, and bromine. And so are these going to be the same molecule? Turns out that they are. Because if you think about it, remember that this Fischer projection on the right represents this bond structure. So again, with the wedged bonds horizontal and the hashed ones vertical. And if you compare these two, you can kind of see that all we're doing is just looking at this from a different perspective. So we haven't changed the orientation of the bonds at all. We haven't changed the relative positions of the bonds in space. All we're doing is looking at this molecule from a different orientation, or a different perspective. So we can figure out that 180-degree rotations are the same molecule. So if you rotate a Fischer projection by 180 degrees, nothing changes. However, if you rotate this by 90 degrees, then we get this projection. And now, so I'm going to draw a little box around. These are the same. So this is the Fischer projection on top and the 3D projection on the bottom. And then for this one we have our Fischer projection on the left side. And our 3D projection on the right. So now, are these the same molecule? So what happens if we rotate it 90 degrees? Well, they are actually not. So although we've rotated it, just like we rotated the 180 degrees, that rotation changes the structure of the bonds in the Fischer projection. Because remember that Fischer projections, we always have the wedged bonds horizontal. So now we've changed which bonds are wedged and which bonds are dashed, which means that we've actually inverted the stereochemistry of that stereocenter. And if that's hard for you to imagine, like I said in the previous video, consider getting your hands on some sort of molecular modeling kit, or maybe a set of free software where you can build molecules in 3 dimensions and really visualize them in space before you can, and that'll help you really get a handle on visualizing stereochemistry and how to look at these molecules, how to get a feel for that. So 90-degree rotations invert stereochemistry. And when we say invert stereochemistry, we're talking about the enantiomer of our original molecule. And if you need a refresher on what an enantiomer is or how do we determine if something is an enantiomer, please consider subscribing to my channel. And if you are already subscribed, then take a look at the previous videos where I've talked about enantiomers and chirality in organic molecules. We can think about one more sort of translation or transformation with Fischer projections. So we've done rotations. Now, what if we take a look at a mirror image, or kind of a flipping of our Fischer projection? So this is our original molecule. And you can imagine this mirror plane and flipping this Fischer projection over that axis. And again, what we've done, so the vertical axis has not changed. We still have the chlorine on top, the iodine on bottom, but now we flip the position of the bromine and fluorine. And that should be a little bit more intuitive to tell you that mirror images also show the enantiomer. So we know that enantiomers are, remember, non-superimposable mirror images of each other. So we have the mirror image of the Fischer projection here. So I can write mirror plane. So these are enantiomers because we've changed the relative orientation of our substituents on the carbon. So let's take just 1 second and practice some more of the absolute configuration, absolute stereochemistry, so figuring out if our stereocenter has an R configuration or an S configuration. So let's take our original molecule here. And this is the Fischer projection, remember, so let's translate that to the stereochemistry projection, or the 3D projective. So remember, horizontal bonds are wedged, vertical bonds are dashed. And if you've never seen any of this, what I'm about to do with priorities or determining absolute stereochemistry around a stereocenter, I also have another video that is an introduction to those priority rules. So our atomic number is what tells us what the priorities are. Thankfully, we don't have any conflicts, so we can just write iodine as our first priority, then bromine, second highest, chlorine, and fluorine with the lowest atomic number. And there are ways to identify the absolute stereochemistry, so R or S, directly from the Fischer projection, but I prefer to translate it to the 3D projection because it helps me understand really where those bonds are and the perspective with which I'm looking at our molecule. So remember, after we do the priorities, so we've assigned all our priorities to the substituents, next we have to place the fluorine, so the lowest priority group, at the rear. So what we can do is maybe imagine rotating this molecule around an axis so we can get the fluorine at the back. So what we end up with here is our fluorine going into the page. Then we have chlorine up here, and now it's going to be pointing towards us since we've kind of rotated this molecule, looked at it from the other side. Then we have our iodine, and finally bromine. And so let's rewrite our priorities here. And now that we have the lowest priority substituent at the rear, so our fluorine, we can look at how the other substituents are arranged. So remember, we go from 1 to 2 to 3, and that points us clockwise. So clockwise is our R enantiomer, or our R absolute configuration. Another way to do this, that sometimes I find a little bit easier, is instead of trying to arrange the molecule or look at the molecule where the lowest priority substituent is at the rear, if you already have the lowest priority substituent towards you, so with that wedged bolded bond, you can follow the same process and then just flip your answer at the end. So here we have lowest priority substituent in front, and then we can follow 1 to 2 to 3. So that gives us an S configuration because it's counterclockwise, but then we have to flip it because we're looking at the molecule from the opposite perspective. So we flip S to R. So in both cases, we get the R absolute configuration. So hopefully that's a little bit of review for you for those CIP or Cahn-Ingold-Prelog priority conventions or nomenclature. The next thing I want to take a look at in this video are diastereomers. And we've already talked about enantiomers. And enantiomers, remember, are non-superimposable mirror images of each other. So diastereomers are also non-superimposable. So again, non-superimposable means that there's no set of rotations or transformations that you can do to make those molecules fit exactly on top of each other. There's always going to be some difference in their 3D arrangement. So diastereomers are non-superimposable, non-mirror images, whereas enantiomers are non-superimposable, but they are the mirror image compounds of each other. And this is going to happen with 2 or more stereocenters. So if you only have one stereocenter, like all of the compounds we've been looking at up to now, then there won't be any diastereomers. But once you have 2 or more, then you'll have both. You'll have enantiomers and also diastereomers. So let's look at an example of what that could be. So let's take a molecule of 2-bromobutane. So we have our butane chain and a bromine on the second carbon. And we know that this carbon is going to be a stereocenter, right? It has 4 different substituents. And we'll say that this is a racemic mixture. So racemic means that we have equal amounts of enantiomers. So we have equal amounts of the bromine with the bromine coming towards us and the bromine going away from us. And let's take a look at a reaction that you may have seen before in some of my earlier videos. Let's chlorinate this with chlorine and some ultraviolet light. And so we could get a couple products out of this, but probably one of the most common or the most abundant product will be the chlorine on this carbon, the adjacent carbon. So what have we done here that's interesting? Well, we still have this stereocenter. That hasn't changed. But now we've produced a new stereocenter. Now that that carbon has a chlorine substituent, it now has 4 different substituents, and therefore it is chiral. There's no plane of symmetry. So what can we do with this? Well, to practice a little bit more, let's draw some Fischer projections. So how are we going to do that? This is a bigger molecule than we just worked with. So let's imagine we can draw our little plus sign here for this compound. And we'll put the methyl substituent. So this carbon is going to be our stereocenter here. So the same as the blue dot up above. Then we have our bromine, and then a hydrogen on that carbon. And then down here, what are we going to do? Well, what we can actually do is just draw another line. So we have 2 carbons here in the middle that we're interested in, and we can just place a hydrogen on both sides of that carbon. So it's not a stereocenter the way we've drawn it, because we know that for this reactant molecule, the 2-bromobutane, we only have the 1 stereocenter. And remember, like I said, we have a racemic mixture. So we're actually going to have a mixture, so a 50-50 mixture of these two Fischer projections. So one with the bromine on the right side, one with the bromine on the left side. And those will be enantiomers of each other. So remember that rotations or mirror image flips of a Fischer projection make the enantiomer. That's what we've done here. We've done the mirror image. So we can draw a few different Fischer projections for the product with the bromine and the chlorine substituents. Let's draw those here. So we'll have 4 different Fischer projections, actually. So let's just draw the skeletons here. And for each of them, we will have methyl groups. Those haven't changed. But now let's draw in our substituents. So for the top row, let's imagine we're looking at this enantiomer of our reactant, so with the bromine on the right, and we've placed a chlorine onto it. So the chlorine can attack from either side, because in our radical halogenation mechanism, we end up with a planar intermediate, and that planar intermediate, since it is equivalent from either side, that chlorine can attack from one side of the radical or the other. So we could end up with this or this, so chlorine on either side. And for the other two Fischer projections, we can imagine the bromine on the left and the exact same thing. So either the chlorine can attack from this side or the chlorine can attack from this side. So let's label these compounds. Compound A, compound B, compound C, and compound D, just to keep things straight. And if I start a new page here, we'll find out that A and D, so these molecules with the bromine and the chlorine on the same side, those are enantiomers. So they have the bromine and chlorine on the same side, so you can imagine those Fischer projections are mirror images of each other. So therefore they are enantiomers. And the same thing for B and C. They are also mirror images of each other. They have the bromine and chlorine on opposite sides this time. However, now we have 2 different stereocenters, right? So what that means is that A and C, so A and C are diastereomers. And the same with B and D. So remember, diastereomers are non-superimposable, but they are not mirror images like enantiomers are. So A and C here are diastereomers because they're not mirror images. We can see that the bromine and chlorine are they're on the same side in compound A and the opposite side in compound C, which means that they are diastereomers. And the same thing for B and D. So one thing is that if we assigned A an absolute configuration to each of our stereocenters, so R or S, we could determine if they were diastereomers or enantiomers by looking at the absolute configurations of each compound. So what that means is if you flip all absolute configurations, so all R to S or S to R, that will give you the enantiomer. So just like we've been assigning R or S to single stereocenters, you can also assign multiple stereocenters. So that just gives you something, for example, if we had 3 stereocenters, we could have a configuration maybe of R, S, R for each of the 3 stereocenters. And if you drew that molecule, and then you drew the molecule with the SRS configuration, that would be the enantiomer, because we flipped all the stereocenters, which means that we will get a mirror image of our original molecule. However, if we only flip a couple of the stereocenters, or just one stereocenter, and we haven't inverted all of them, so maybe we change the last one to an S, but we keep the first 2 the same, that will be a diastereomer. So just like we've looked at on this side with these 4 molecules, if we flip just one of the stereocenters, for example, from A to C, what we've done is we've flipped the stereochemistry of the carbon with the bromine on it, so it's moved to the other side, but we've kept the stereochemistry the same for the carbon with the chlorine substituent. So we've only flipped one stereocenter, which means that those are diastereomers. Whereas from A to D, we flipped both of those stereocenters, so now the bromine and the chlorine are on the opposite side, so those are enantiomers. And this applies for any number of stereocenters. Usually we'll only work with maybe 1, 2, maybe 3 stereocenters at once, but it is general. And finally, just to note, diastereomers actually have different physical and chemical properties. Which is important to note because enantiomers do not, save the few exceptions I talked about in the previous video. Diastereomers will have different boiling points, different melting points, a lot of times different densities, different reactivities, things like that. And you can separate them fairly easily, whereas with enantiomers, it is extremely difficult to separate them. So that concludes my video on Fischer projections and diastereomers. My next video will be on meso compounds, so still looking at compounds with multiple stereocenters, as well as how to separate enantiomers and some methods of doing that. So again, thank you very much for watching, and please like and subscribe to my channel, and also please consider donating to my Patreon page, which I will link in the description.